Hi, Integrated Mathlon. Welcome to lesson 2.4.1b. We're on day 2. So last time we were doing distance formula, and it was related to Pythagorean Theorem and figuring out how to find the distance between 2 points on a coordinate plane. We're going to keep doing some more of that today. We're going to use it a little bit today to help us out with some triangles and some quadrilaterals. We're going to do activities 1.2 and 1.3 in your book, so make sure you're on page M2-253 to get this party started. So as I said, we're going to analyze triangles that lie on a coordinate plane. We're going to classify them by their properties. So just remember that you can classify a triangle by its sides. It's either scalene, meaning it has no congruent sides, isosceles, meaning it has 2 congruent sides, or it can be equilateral, which means all 3 sides are congruent. And of course, we can also classify a triangle by its angles. If it has an obtuse angle, it's an obtuse triangle. If it has one right angle, it's a right triangle. And if it has 3 acute angles, it is going to be an acute triangle. So we're going to play with that today and just get a little more into this. So here we have triangle ABC. Try point A, B, and C. You may even want to make a quick note of what those points are. That wouldn't be the worst idea in the world. It looks like A is at 0, -4. It looks like B is at 0, -9. And it looks like C is at -2. I had to go left 2, down 5, so it's a -5. So that just might be helpful to you to just kind of have that written down as you go. So here's what I would like you to do. I would like you to consider the sides of triangle ABC and describe it as scalene, isosceles, or equilaterals. So scalene, no sides are congruent. Isosceles means you have 2 congruent sides, and equilateral means you have 3 congruent sides. So go ahead and find the length of each of these sides. You may need to use a little distance formula to do that. That's okay. Work this out and then hit play. So hit pause to work this out, find your sides and classify it, and then hit play when you're ready to check your work. So again, it helps if you have the points written. We said this was 0, -4. We said that this was 0, -9. And we said that this one was -2, -5. Now for AB, I actually don't need to use distance formula. Do you see how it's vertical like that? If it's vertical or horizontal, I can just count it to figure out how long it is. So that means from A to B, I go 1, 2, 3, 4, 5. So it looks like side AB is 5 units long. Side AC though, I'm gonna need to use some distance formula there. It's kind of on a slant, right? So remember distance formula, you subtract your x coordinates and you to square it, and then you subtract your y coordinates and you square it. So watch those negatives. So when I set it up, it looked like this. I did 0 minus a -2, and then I did -4 minus a -5. Clearly, there's a lot of cleanup to be done here. We know double negatives become positive, so 0 plus 2 means it's going to be 2 squared. Double negative becomes a positive. -4 plus 5 means that will be a 1 squared. So 2 squared is 4, 1 squared is 1, and 4 plus 1, of course, gives us 5. I didn't know the square root of 5 off the top of my head, so I grabbed my calculator and I rounded to the nearest 10, and I got 2.2. So these 2 sides are not congruent. Good to note. Let's now take a look at side BC. So again, my x coordinates, subtract those guys. My y coordinates, subtract those guys, right? That's our first thing we have to do. So I did 0 minus a -2, and then I did -9 minus a -5. Remember, it doesn't matter which one comes first. It'll all work itself out in the end. So that double negative becomes a positive. So 0 plus 2 makes that 2 squared. Double negative becomes a positive. So -9 plus 5 will make that a -4 squared. 2 squared is 4. -4 squared is a positive 16. 4 plus 16 is 20. And again, I grabbed my calculator. I got about 4.5. Which is not the same as either of these. So I have a side that is 5. I have a side that's 2.2, and I have another side that's 4.5. Guys, none of these sides are congruent. which means our triangle is scaling. Yay. All right. What about the angles though, right? We said you could also classify a triangle by its angles. That sounds to me like you need to find the slope for each of these lines. So go ahead and find the slope for each of these lines to try to figure out whether or not this is a right triangle. Go ahead and hit pause, find all your slopes, figure out if it's a right triangle, and then hit play when you're ready to check your work. All right. First of all, this guy right here, AB, is like straight up and down. Remember what we call a slope of a vertical line? We say that it is undefined. Do you remember that? Do you remember that? Maybe, perhaps. Let's now find the slope of AC, and we always go left to right when we do slope. So it looks like I went up 1 and over 2. So I rose 1 and I ran 2. So it looks like the slope of AC is 1/2. And now let's do BC, but again, we go left to right. So I actually have to start at C, and notice that means I have to go down 4. So I went down 4, which is negative, and then I'm going to go right 2, which is positive. So I went down 4 and right 2. Oh, and negative 4 divided by 2 is just a negative 2. Hey, do you notice? Do you notice that negative 2 technically could be negative 2 over 1? Do you see how those are opposite reciprocals? One of these is positive, one is negative, and 1/2 is the reciprocal of 2 over 1. Oh, what does that mean? Hey, it means that these two lines, AC and BC, are perpendicular. Oops, sorry, my little button didn't want to work there. They're perpendicular. Yeah, segments AC and BC are perpendicular. Their slopes are opposite reciprocals. So triangle ABC is a right triangle. Hey. You know what though? There's actually another way to figure out whether or not something is a right triangle. So let's see what Zach did. So Zach used the Pythagorean theorem to determine whether triangle ABC was a right triangle. So he set it up like this: a squared plus b squared equals c squared, square root of 5 squared plus the square root of 20 squared. He didn't use decimals. Equals 5 squared. So a square and a square root cancel out, so that becomes 5. Square and a square root cancel out, so that becomes 20. And 5 squared is 25. Oh, and 5 plus 20 equals 25 as well. So why is Zach's reasoning correct? Why did this work? Go ahead and hit pause, jot down your thoughts on that, and then hit play when you're ready to check your work. So Zach's reasoning is correct because if you recall, we talked about it last time, the Pythagorean theorem only applies to right triangles. The Pythagorean theorem only works on right triangles. So you take your biggest side, you plug it in for C, and if it works, it's a right triangle. So since the side lengths of triangle ABC satisfied the Pythagorean theorem, Zach proved that the triangle ABC is in fact a right triangle. So instead of using the slopes, we can actually use the sides to figure out if our triangle is right, acute, or obtuse. Do you want to see? So you can use the relationship among the sides of a triangle to determine whether a triangle is acute or obtuse, and it's all about that Pythagorean theorem. So given that A, B, and C are sides of a triangle, and please notice, this is important, you might even want to underline it in your book, with C as the longest side, here's what happens. You're going to do C squared and A squared and B squared. If your C squared is too small, think of it as Goldilocks and the Three Bears, people. If your C squared is too small, if your C squared is less than A squared plus B squared, you are dealing with an acute triangle. If your C squared is too big, right? C squared is greater than A squared plus B squared, you are dealing with an obtuse triangle. But of course, if your c squared is just right, c squared equals a squared plus b squared, you're dealing with a right triangle. So this is an awesome trick because you can actually use the sides of a triangle. Just make sure that when you put that c is your longest side, whatever the longest side is, that's going to be your c. Plug it into that Pythagorean theorem and see what happens. If it's equal, it's a right triangle. If it's c squared is too small, it's an acute triangle. And if c squared is too big, it's an obtuse triangle. So go ahead and try this out. We have like 3 of them for you to try over here on number 2. I would like you to use these side lengths to determine whether or not they create an acute, right, or obtuse triangle. Go ahead and use that method we were just looking at with the Pythagorean theorem. So hit pause, work this out, and then hit play when you're ready to check your work. All right, how you doing? So I'm looking at these 3. And 42 is clearly the biggest one. So I'm going to make that my c squared. All right, 42 is the biggest one, so that's going to be my c. So fine, that means I need to do 42 squared, and then on the other side, I'll do 36 squared plus 15 squared. For now, I've put a question mark in the middle because I don't know if it's going to be equal to, less than, greater than, like I'm not sure what's happening here. So for now, I'm leaving a question mark in the middle, and I'm grabbing my calculator. 42 squared is 1,764, 1,764. 36 squared is 1,296, and 15 squared is 225. And then I went ahead and added this side together, again, using my lovely calculator. 1,296 plus 225 gave me 1,521. Well, that means my c squared is too big. 1,764 is greater than 1,521. And since my c squared is too big, it's an obtuse triangle. Let's take a look at B. Again, I'm looking at these 3, and 18.5, that's definitely the biggest one. So I'm going to do that over there. So let's go ahead and put everybody in. So instead of c squared, we'll do 18.5 squared. And then on the other side, we'll have 11 squared plus 15 squared. And again, using my calculator, 18.5 squared gives us 342.25. And on the other side, of course, we have 11 squared, which is 121, and 15 squared, which is 225. If I add these guys together, 121 plus 225, I got 346, which is a little bit bigger than 342.25, right? 346 is a bit bigger than that. So that means my c squared is less than my a squared plus b squared. Well, look at that. If my c squared is too small, it's just a little too small, but it's still too small. Since my c squared is too small, it's an acute triangle. For this last one, I had a hard time because of that root 65. So I'm grabbing my calculator here. The square root of 65 is about 8.1. Oh, hey, and so C needs to be my biggest side. So that means that this is going to be, oh, sorry, my pen went nuts. I'll fix it. That means that that square root of 65, that's going to be my C. That's the biggest one. I'm not going to do decimals, though. Let's just leave it as a square root of 65 for now. So square root of 65 squared, and then I have 4 squared plus 7 squared on the other side. Well, we know that squares and square roots cancel each other out. So the square root of 65 squared is just plain 65. And of course, 4 squared is 16, and 7 squared is 49. And again, you can use your calculator. 16 plus 49 gives us 65. 65, it's perfect. It's just right. So because our c squared equals our a squared plus b squared, we are dealing with a right triangle. So I find that I like using this way to figure out what kind of a triangle it is based on its angles. I like using this Pythagorean trick for it a little bit better than finding all the slopes. Finding all the slopes is work. I like using the Pythagorean trick. It's a little bit better. So if your c squared's too big, it's obtuse. If your c squared's too small, it's acute. And if your c squared is exactly equal, just right, it is, of course, a right triangle. So with this in mind, we've got a new one for you to play with. So first of all, go ahead and graph triangle JKL using these points, -2, 4, 8, 4, 6, -2. So just start off just by graphing it. And again, I really, really recommend using a straight edge to draw it as suggested off to the side. So ruler, straight edge of some kind makes it easier. So go ahead and hit pause and draw your triangle. Make sure you label JK and L, and then hit play when you're ready to check your work. All right, so point J is at -2, 4. So I have to go left 2, up 4. And I'll put my little dot there and I'll call it J. K is at 8, 4. So that means I have to go right 8 and up 4. Put my little dot there and I'll label it K. And L is at 6, -2. So I have to go right 6 and down 2. Put my dot there and I will label it L. And of course, use a nice little straight edge to connect the sides all up. Yay. There's our triangle. It's so pretty. You know what I'm about to ask you to do, right? I'm just saying, you know what's coming. So we're going to classify triangle JKL. So first thing you're going to do for part A here on number 4, you've just drawn the triangle, you have the points. First thing I want you to do is I want you to find the sides of triangle JKL. Just like we did on the other problem, find the lengths of the sides and then decide whether your triangle is scaling, isosceles, or equilateral. Go ahead and hit pause to work your way through that and then hit play when you're ready to check your work. So as always, math teachers, we're lazy whenever possible. And I noticed that with JK, just kidding, I could actually count how far across it was. So I did. I was like, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I was like, oh, that's easy. JK is 10. Remember, if it's horizontal or vertical, you really can just count to figure out how long that piece is. Now for KL and for for KL and for JL, we have to do a little bit more work. I did have to use some of that lovely, lovely distance formula action. So for JL, so for KL, I'm going to do 8 minus 6, and then I'll do 4 minus a -2. And then I'll work it out from here with my lovely distance formula. 8 minus 6 is, of course, 2, so that will be 2 squared. 4 minus a -2, well, double negative makes that a positive, so 4 plus 2, that means that will be 6 squared. So 2 squared is, of course, 4, and 6 squared is, of course, 36. 4 plus 36, Miss Scott doesn't know how to write. I have a mistake here, don't I? Hang on, guys, I can fix it, though. Do you want to see my math skills? I have math skills. I can fix it. I can fix it. 4 plus 36 is, of course, not 50. It is, of course, 40. That means I got to fix something else here, though. Hang on. I got it. Easy fix. Boom. All right, we'll try this again. There we go. And, of course, 4 plus 36 is 40, and the square root of 40, using my handy-dandy calculator, is 6.3. Sorry about the mistake there. JL, we need to do JL as well, right? So let's do JL. Let me come back up here. So for JL, I'm going to do -2 minus 6, and then 4 minus a -2. And let's see then, -2 minus 6 gives me a -8 squared. And, double negative. 4 minus a -2, no way, baby. That becomes 4 plus 2, which is 6. So that will be 6 squared. -8 squared is, of course, 64, positive 64. And 6 squared is a 36. 64 plus 36 is 100. I know this one. I didn't even need my calculator for this one. The square root of 100 is 10, because that's the number of times itself that'll give you 100. Hey, do you see it? Look. That means that 10 And 10, I have two congruent sides. My triangle is isosceles. Yes, it is. All right, so go ahead and beautiful. So now we know that it's an isosceles triangle. We've classified it by its sides. Let's classify it by its angles. We want to know if our triangle is acute, obtuse, or right. You might want to use our little trick from earlier with that Pythagorean thing. I would really recommend it. Go ahead and hit pause to figure this out. Use that Pythagorean trick, figure out if your triangle is acute, obtuse, or right, and then hit play when you're ready to check your work. All right, so we had a side that was 10. We had another side that was 6.3. Actually, I don't want to write 6.3. Let's leave it as a square root of 40. That'll be easier to use in our formula. And then we had another side that was 10. So that means my longest side is 10. I mean, yeah, I get it. I have two of them, and maybe you already see the problem. But let's make that our C. So I have 10 squared plus 10, yeah, and I don't know if it's equal to, less than, or greater than 10 squared plus the square root of 40 squared. So this is just like we did before. Of course, 10 squared is 100, 10 squared is 100, and we know that squares and square roots cancel out. So the square root of 40 squared is 40. And 100 plus 40 is 140. Uh-oh. Our C squared is too small. Look at that. 100 is less than 140. So because our C squared is too small, this must be an acute triangle, has 3 acute angles. So I love this Pythagorean trick. It's so cool, right? Too big, too small, just right. It's got that Goldilocks vibe, Goldilocks and the Three Bears vibe going on there. But hey, it helps me know what kind of triangle I'm dealing with. So finding the sides of your triangle, super helpful. Not only does it tell you scalene, isosceles, or equilateral, you can also plug it into that Pythagorean theorem to figure out if it's acute, obtuse, or right. Kind of a nice trick. All right, so we've already been classifying quadrilaterals by their sides and angles. And if you still have those little cutouts that we made during our getting started activity last time, you might want to have those handy because we were making notes on those to help you classify your quadrilaterals. Remember, quadrilaterals have 4 sides now. But you can classify quadrilaterals by their sides and angles, right? I mean, if it has 4 congruent sides, if it has 4 congruent angles, if the opposite sides are parallel, right? Or if it has 1 set of parallel sides. We know all these things to help us classify our quadrilaterals. So we can use this information to compose quadrilaterals on a coordinate plane. We're actually going to make them. That's right. So we're going to analyze these points. I've got A, B, and C. Suppose that I want to put some point D such that I want a quadrilateral A, B, C, D, wherever D is out here, to be a square. All right, so I want to put a 4th point out here, a point D, to make this a square. So consider the properties of a square, right? You guys know things about squares, what squares are, what they do. So how does knowing that a square has 2 pairs of parallel sides help to determine the unknown location? How could that help you out? Go ahead and hit pause and just jot down some thoughts on that, and then hit play to keep the discussion going. So because each pair of opposite sides of a square are parallel, that means that they have the same slope. So if I can find the slope for AB, that should tell me what the slope is for CD over here, right? And same for the other way around, right? If I know the slope of BC, that should tell me the slope of AD and wherever AD is hanging out there. Good to know these things. So we can totally use that slope to the slope of AB to draw us the slope of DC and just kind of draw it out. And then, of course, if I know the slope of BC, we can draw that same slope coming out this way and look at where they intersect. That will be our 4th vertex, D. Well, how does knowing that a square has 4 right angles, how would that help you, right? Squares have 4 right angles. So how would that help you find the unknown location? Go ahead and hit pause, jot down your thoughts on this, and then hit play to check your work. So for right angles, that means our lines have to be perpendicular, right? If these lines are perpendicular, pew, pew, then we know that our slopes are opposite reciprocals. So the consecutive sides have slopes that are opposite reciprocals. Oh, so that means that we can use the slope of AB to draw the next side over for AD, right? If I know his slope, do the opposite reciprocal, that's going to be the slope for AD. Same thing over here, right? If I know the slope for BC, do the opposite reciprocal, and that will give me the slope for CD. And again, where they intersect, that's going to give me my point D. So now that you've got two different ideas, two different ways of approaching this, go ahead and determine the location of point D. You are going to want a straight edge to help you do this. You're probably going to want to find the slopes of AB and the slope of AB, slope of BC. That'll make things easier. And then, of course, use your straight edge to draw it out and find where they intersect. Find your point D, plot it, label it on the coordinate plane. Go ahead and hit pause to work this out, and then hit play when you're ready to check your work. All right, so I'm going to use the parallel thing because I like that. Parallel's easier. Like I know if I know the slope of AB, it should be the same as the slope of CD. So let's find that slope of AB. So to remember, we go left to right. So to get from B to A, I have to go up 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I had to go up 10, and then I had to go over 1, 2, 3, 4. So it looks like the slope of AB is 10 over 4. Yes, I know you could simplify that if you wanted to. If you wanted to, you could be like, but the slope is actually 5/2. You could do that, but I'm not worried about it right now. So since the slope of AB is 10 over 4, the slope of CD should also be 10 over 4. So I should go up 10, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then over 4, 1, 2, 3, 4. And then I'll go ahead and connect it. Sorry, I didn't get over far enough. Miss Scott can't count. Sorry. So there's CD. That's good. Now let's do the other side. So slope of BC should be the same as the slope of AD. So let's take a look at the slope of BC. It looks like to get from B to C, I have to go down 1, 2, 3, 4. So that's a -4, right? I had to go down 4. And then over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like the slope of BC, which is the same as the slope of AD, is -4 over 10. And again, I know if you really wanted to simplify, you could say it's -2 over 5. But for purposes of making it easier to graph, I'm going to leave it like this. So let's do AD then. I have to go down 4. 1, 2, 3, 4. I have to go over 10. Oh dear. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then we'll connect them up and call that point D. And it looks like the coordinates, I had to go right 5 and up 3. So the coordinates of point D are 5, 3. And of course, I can erase all of that stuff and make it prettier. Now it's all pretty. That's why I like to use a pencil. Erase it, make it prettier. So yeah, so that wasn't so bad, right? I just used the slopes that I had to make my new lines. No big deal. That was nice and easy. So using these same original 3 points, let's try something else. And by the way, we already know that D is at 5, 3. So I know that D is at 5, 3. That would make it a square, right? But notice it doesn't want a square anymore. So using the same locations for points A, B, and C to identify the location of a new point E. And notice we want quadrilateral ABCE as to be a trapezoid with only one pair of parallel sides. So I don't want D anymore. I want some point E that's going to make that a trapezoid. So identify any information that's helpful to locate point E. Just explain your thinking here. Go ahead and hit pause, jot down your thoughts, hit play when you're ready to keep going. So my thought was I was thinking about that whole one pair of parallel sides thing. And so I need to decide which two sides from my original quadrilateral ABCD, which two do I want to keep parallel, right? Will I keep AD and BC parallel, or am I going to keep AB and CD parallel, right? I need to know, is it these two sides that I want to be parallel and I'll just make him a little longer, a little shorter? Or is it these two sides I want to be parallel and make him a little longer or a little shorter so that the other set isn't parallel? So can you just real quick describe then possible locations? Because there's no one right answer here, right? There's actually a lot of right answers. So describe the possible locations of point E, such that quadrilateral ABCE is a trapezoid with only one pair of parallel sides. Go ahead, jot down your thoughts, and then hit play when you're ready to keep the discussion going. So we don't want it to be point D, right? Because of course, if it's point D, then that doesn't work for us too well because that makes a square. We don't want a square. We only want one pair of parallel sides, not two pairs. So I was thinking of a few things. First of all, I thought to myself that point E can be anywhere on D. The line AD, like if I were to make that go forever and ever, it can be anywhere on this line except 5, 3, right? If I put point E right here, that would definitely make me a trapezoid, wouldn't it? If I should have made that a solid line, that would have been easier. If I decide, I want to put point E over here, that's fine. That would still make us a lovely trapezoid. But it can't be D. So a little closer to A, a little further from A, E can be on either one of those, and you'd be all right. The other way to approach this, because this is not the only way, it's not the only way. The other way to approach this is to say, and again, here's point D, just as my point of reference here. The other way to approach this is to say that E can lie anywhere on CD. And we'll make it a big old line. This is not my best drawing. My other drawings are better. There's point D. But E can be anywhere above C, right? E can be over here. Like I can make E over here and be like, there's a trapezoid, woo! Or I could make E be over here and I'm all like, there's a trapezoid, woo, there's my E. Just so long as I don't put it at point D, we should be okay. So we have some options available to us here. That's very nice, isn't it? As always, guys, I hope you found this helpful and I hope you found this useful. If you have questions or concerns, please let me know. Use that Ask for Help button in the breakout room or come see me during office hours or ask me in class, something. Let me know how I can help you out and I'll see you guys later. Bye.